Alright, so my video is actually turned off, so okay, so let me do the solution for this question here, okay? Alright, so first of all, the way you do problem in physics, always write down the given information. Here we are given this height, right? So let's call this label it just as h1. Here we are given we are also told something about the open end. So first question is, we are said PM equal to what? What's the pressure of the gas inside this chamber, right? That is the first part. And then we are told, assume the density of the marker is what? Rho Hg equal to 13,600 kg per meter cube. Okay. And we are also given this h1 equal to 20 centimeters. I'm just going to convert that to meter here and write that 0.2 meter. P area, the right side on the tube is, this tube is open to the air, so it has a P is really P naught or P atmospheric pressure, so P ATM equal to just 1.013 into 10 to the power 5 Pascal. Okay, so now how do you find the pressure here? What is the pressure inside? So you guys already know this, right? So let's look at the problem. Let me explain it here on the picture, and then I'll show you the solution over there, okay? So, these two guys are at the same height, so, we can use some information. If we get some information here, we can use that information here, and then whatever the information we have here, we can use to find the pressure here, okay? So let's look at on the right hand side first. At this height, so let's call this as 0.1, okay? Reference point 1. I'm going to just label this as 0.1, and then I'm going to just take that same height here and then label this point as 2 here, okay? Those are the two different points. Now, forget about everything, we have it here for now. So see, at 0.1 we can find the pressure due to this atmospheric pressure as well as due to the pressure due to the column of this mercury, right, at this height, okay, H1. So and then we know this fluid here is at hydrostatic equilibrium, so we can use the hydrostatic pressure equation, okay. Once we know the pressure here, this 0.1 here is this reference point 1 here is at the same height as this point 2, right? Same horizontal height. And so we can use that pressure we have at point 1, that must be equal to the pressure at this point 2, okay? So once we know the pressure at point 2, which is also linked to the gas in the chamber, so the pressure at point 2 must be same as the pressure of this gas in the chamber. So we should be able to solve this problem, okay? So now let's do it here, steps. So using hydrostatic pressure equation, EQN means equation, okay? We can write, let's call this pressure at point 1 as P1 equal to what? P ATM, right, atmospheric pressure, plus rho density GH, okay? But this rho is not a water, here we have a mercury, so let's write a rho Hg, and G doesn't change, H is the height, we said that is labeled as H1, okay? Now we wanna just write the value here. What is the P atmospheric pressure? 1.013 into 10 to the power 5 Pascal, plus, this is not given to you in the equation, but by now you should be familiar with it, or at least you will be given in the equation set. That's the constant, okay? So plus, what is the density of mercury here? We are given that is 13,600. So 13,600 times 9.8 for the value of G times the height, which is 0.2. What do you get here when you calculate this? When you put that in your calculator, do you get 1.3 into 10 to the power 5 Pascal? Okay, so this is P1. Let's put a box because this is not our final answer, but this is something we need to look at again. Okay, so that's P1. Let me check if this my camera is still shooting my video. Okay, it is shooting. Okay, so this is the pressure at this point, right, due to this column of the Mercalli as well as the atmospheric pressure. Now we said that pressure at point 1 must be equal to the pressure at point 2 because both of those are at the same height for this liquid here, right? So I'm going to erase this part, okay, because I need more space. From here, let us go here. So P1 must be equal to P2 since point 1 and 2 are at same horizontal line. Okay, this is the reasoning I'm writing for why I'm saying the pressure at point 1 is equal to point 2, okay? So then P2 must be equal to the same pressure. Let's not write that down yet. What we also know is also, let's call this equation, I don't know, yeah, well we don't need to call equation yet. Also P2 also, not P2, point 2 is in contact with gas. Therefore, PM, pressure of the gas, okay, PM must be equal to P2. And this must be equal to P1, right? So which is what? 1.3 into 10 to the power 5 Pascal. Alright? So this is the final answer here. Okay? So therefore Pm is equal to 1.3 into 10 to the power 5 Pascal. So this is the final answer. This is the pressure of the gas inside the chamber, right? So you see this is a little bit greater than the atmospheric pressure, right? Because we also have a mercury over, I mean, that's a gas pressure here, right? So it's not open to, this is not open to the air, okay? So this gas has a higher pressure than the atmospheric pressure. Okay, so that's the pressure inside the chamber. So please finish copying this part, and then we'll look at one more problem. Alright. Okay, so let's look at one more question here. Question 2. So I'm going to write this question here and then make a graph, okay? The following graph shows the position versus time for a mass attached to a spring constant. K equal to 200 Newton per meter, undergoing damped simple harmonic motion. Okay, so let me draw this graph over here. I need actually quite a, okay, so here. How about this? Let's copy this question and then I'm gonna make a graph. Okay, so you get to see the bigger graph. Alright, I'm going to erase this, okay? So for this question, I'm going to make a graph here. And the graph is like this. One, two, three, 4, 5, 6, and so on. And then we have here 1, oh, that's not 1, that's, so this is the time in second here. On this axis, horizontal axis, in the vertical axis we have a position x in meter, okay? And we have this as a 0.2 seconds, 0.4 second, 0.6 second, 0.8. We have, this is our 0, we have the same thing here, but negative. X is 0.4, minus 0.4, minus 0.6, and minus 0.8, okay? And then the graph starts at this point, so I'm gonna just put a dot before dot at first so I can draw it nicely here. 6 goes through 1, and then this goes almost up to 0.5, and then it goes here, so almost down here. And then it picks at 0.4 at 4 seconds, so 4 seconds at close to 0.4, and then it comes back through 5, and then goes here, okay, 0.5, and then from 0.5 it goes all the way down to 5 at 6 seconds, wait, 4, okay, at 6 seconds, and then it goes, 6 seconds is at 0.3, so that's kind of about, not here, let me write this 6 a little bit up, 6, oops, yeah, 6 up, so it's kind of here, we don't really need this part of information, at least for this question, so, alright, so let's try to draw these like this, okay? Alright, so that is the graph we are given. So the question goes this, so from this graph, from the graph determine A, the frequency of oscillation. I'm just going to write the entire question. From the graph determine find the frequency of the oscillations. Okay, so let's do work on this. So please try working on this. How can you determine the frequency of oscillation? I want to emphasize this point corresponds to about here, about 4, okay, not about 6. I don't know how you see in the video, so 0.4 there. Alright, so please determine the frequency here from this graph. Okay, did you find the frequency? So here, frequency equal to what, right? So we know frequency f equal to 1 over t time period, and from graph we can see t equal to what? What's the period here? So you start from here, goes down, comes back, and then gets to the peak again, right? So how long does it take to peak again? So that's our period, right? From origin here all the way to, so if you look at that goes to about 4. So this time is, which is 4 seconds, okay? So that's the period. After 4 seconds, again it repeats, right? So, of course this is the damp oscillation and it has a now different amplitude, but the repetition, the period is same, constant here, 4 seconds here. Which means frequency is what? F equal to 1 over t, which is equal to 1 over 4 seconds. That's 1/4 hertz. Okay, so that's the frequency. Okay, all right. So please finish copying this, and I'm going to write another question here, right here. Okay, so another thing you want to determine is determine the time constant of for the decay of oscillation. Excuse me. Oscillations, okay? So when it's a time constant, what is it asking here? We are supposed to find tau equal to what? Time constant. Remember? So we know we have to do several steps, right? Tau, we cannot just look at the graph and just write the information here, so we have to do a few things. So take a moment if you can work on this part here. Take a few minutes. Okay guys, I'm gonna turn off this video because